in reality, as well as in theory, many acid-base reactions are essentially equilibrium reactions. Let's have a look again at hydrochloric acid dissolving in water. So we have already seen that hydrochloric acid behaves as an acid, donating a proton to the water molecule. That's supposed to be a Q. And water behaves as a base by accepting it. Now, there is the possibility that the chloride ion could accept a hydrogen ion and turn itself back into HCl. However, the likelihood of that happening is very, very, very small indeed. So essentially, the position of equilibrium in this reaction lies very, very strongly to the right. This is one reason why hydrochloric acid is described as being a strong acid. However, if we were to take ethanoic acid as an example of a weak acid, so weak acid, let's have a look at ethanoic acid. So here we've got CH3COOH reacting with water to form the ethanoate ion plus the oxonium ion. Ethanoic acid is behaving as the acid because it is donating its proton to water. So in this particular case, water is behaving as a base. But in this particular example, as is the case with all weak acids, the position of equilibrium actually lies fairly strongly to the left, which means that we have a solution in which we are going to have a few ethanoic acid molecules, lots of water molecules clearly, they're in excess, a few ethanoate ions, and a few oxonium ions. The majority of the ethanoic acid molecules do not dissociate. They do not ionize. That means, of course, that because the concentration of hydrogen ions or oxonium ions in solution is very, very low, weak acids have a much higher pH, round about pH 4 or 5, as opposed to strong acids like hydrochloric acid, where we have full dissociation. We have a very large number of oxonium or hydrogen ions in solution, and so the pH, which is a kind of measure of the amount of acidity, is much lower, pH 1 or 2 for a strong acid. If the equilibrium for a weak acid in water lies very strongly to the left, then that implies that this ion here, the ethanoate ion, is going to readily be able to accept a proton from the oxonium ion and move back to being ethanoic acid. In which case, the ethanoate ion is behaving as a base because it is accepting a proton from H3O+. H3O+ becomes H2O. The ethanoate ion becomes ethanoic acid. We can pull all this together by describing this in terms of acid-base pairs. What we say is that the ethanoate ion is the conjugate base of ethanoic acid, and H3O+ is the conjugate acid for water. Let's have a look at another example. If I take HSO3-, it is happy to react with water to form SO3-2- and our oxonium ion, H3O+. In this case, if we have a look, we can see that HSO3- is behaving as the acid because during the course of this reaction it donates its proton. And as a result of that, it becomes SO3 2-. So SO3 2- is the conjugate base. We can say that HSO3-, SO3 2- are a conjugate acid-base pair. Similarly, if we take water, water is behaving as a base because during the course of this reaction it accepts a proton from the acid. So water is the base and H3O plus here is the conjugate acid. So there is the possibility that H3O plus could donate a proton to SO3 2-. HO3, the oxonium ion, would behave as the acid, SO3 2- would behave as the base, and we'd be back where we started. It's absolutely crucial that we appreciate that we are describing behaviour here. We're not giving substances definitive labels. Let me explain why. If I were to take my HSO3- ion and react it with H3O plus, then this is what happens. We get H2SO3 and water. So in this particular case, HSO3- is not behaving as the acid, it's behaving as a base because it's accepting a proton from a stronger acid during this reaction. So in which case, HSO3- is the base, H2SO3 is my conjugate acid. It has the ability, depending on conditions, to donate a proton back to water, so we end up back where we started. H3O plus is my acid because during the course of the reaction it donates a proton to SO3- and we end up with water. So this is my acid and H2O becomes the conjugate base. So acid-base pairs, conjugate acids and bases, we're describing the behaviour of substances. We're not giving them definitive labels. Okay, so pulling all this together. My top example here, hydrochloric acid. Hydrochloric acid is a strong acid, which means that the position of equilibrium in this reaction lies very, very strongly to the right. To all intents and purposes, hydrochloric acid is fully dissociated. What this means in practice is that strong acids tend to have very weak conjugate bases. The likelihood of the chloride ion behaving like a base, picking up a proton and returning to HCl is very small indeed. If we take an example of a weak acid, something like ethanoic acid, we see that it has a fairly strong conjugate base. The likelihood of the ethanoate ion accepting a proton and returning to ethanoic acid is really quite high indeed. The position of equilibrium in this particular case lies very strongly to the left. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.